Okay, ladies and gentlemen, so let's get started with our class for today. And today we are going to continue to discuss the development of the new atomic theory. And today we're going to talk a little bit about Niels Bohr and the development of his theory, along with a little bit of what Einstein proposed. So, without any further ado, the first thing I'm going to do is I'm going to review a little bit of where we left off in our last video. And in our last video, we were talking about the photoelectric effect. And basically, summarizing, the photoelectric effect refers to the emission of a metal when light shines on the metal. So basically, uh, to illustrate that real quick, the photoelectric effect is if you have a metal and then you have a beam of light, uh, shining on it or hitting it directly. The photoelectric effect says that as light hits at it at a specific frequency, that's going to cause the metal to energize and release an electron, right? So that's what the photoelectric effect was. That's what it meant. Okay. So that being said, we'll go back to that real quick. Give me one sec, guys, just so I don't delete anything I'm not supposed to. Okay, so that's where we left off. So we know that if light hits metal at a specific frequency, it's going to cause an electron to transfer. But it says that the wave theory of light, what that led to the development of the wave theory of light, it says it did predict that light of any frequency could supply enough energy to eject an electron, but didn't quite fill in the gaps in terms of how or why or if that varied from specific metal. And then you have Max Planck, who was a German scientist, and Max Planck proposed that objects emit energy in small specific packets called quanta. So actually it was Planck who came up with the idea of quanta, which is pretty much how much energy an electron gains or loses. And he proposed that depending on the metal, depending on the frequency, they release a specific amount of energy. It's not like a one size fits all. It's what he pretty much proposed. And basically, quantum of energy is defined as the minimum amount of energy that can be lost or gained by an electron. So it not only refers to how much energy is lost, but also how much energy is gained. And that's what Max Planck proposed, that they release a specific amount of energy and a specific amount of frequency. And he proposed his very famous equation, which E equals hv, where h is Planck's constant, and v is the frequency, and Planck's constant is actually 6.26 times 10 to the power of negative 34 joules per second. That's what Planck proposed, is a 4. That's what Planck proposed for his theory, okay? Or what's known as Planck's constant, which still stands today. Einstein actually went on and expanded on this. It says Einstein expanded on Planck's theory by proposing that light can act as a wave and as a particle. So what Einstein said was he studied Planck's theory and he suggested, well, the reason why electrons are gain or lose energy in specific small packets, or the reason why it may vary, is not just because light acts as a wave, but it also acts as a particle. So light doesn't necessarily have a mass, or can't be measured quantitatively the same way you would measure grams of an object. But that doesn't mean it doesn't occupy space. It just means that it acts both as a wave and as a particle. And this is, of course, accepted today. And Einstein not only expanded on Planck's theory, but he also came up with his version, which is that E equals mc squared. very famous equation that we all know or have heard of. And it says that and then we go on to read further down in the section. It says that the lowest state of the atom is the ground state. When an atom has a higher potential energy, they are in the excited state. And let me try to illustrate that. So we kind of have to think of this, and we'll see it in a minute when we talk a little bit about Planck's, I'm sorry, not Planck's, Bohr's theory. But you have to look at atoms kind of as if they were a ladder. And when you have a ladder and you go up a ladder, they're called the rungs of a ladder, right? When you climb a ladder, you know that a ladder, if you're in the lowest rung of the ladder, you're at the lowest state. And as you climb up, so the same thing is, and then as you climb up, the higher you go. So it's kind of like the same thing. The lowest possible or energy level of an electron or an atom is called the ground state. And as energy is applied to it and energy is gained, it goes up the ladder. And then as it goes up the ladder, we say that it is in what we call an excited state. So a ground state, using this as a reference, is when the atom is at its lowest energy level, and an excited state is when that potential energy increases and atoms go up higher in that energy level. Okay, so that's pretty much what that statement is trying to explain in terms of the energy level of an atom. And moving on to understand this a little bit later, it says that using this, scientists actually discovered what is known as the emission light spectrum. And it says that the emission light spectrum was discovered when a narrow beam of light was passed through a prism and emitted four specific colors. So as I mentioned in class, light is not just this white beam that we see, but rather it is a expressed, I guess, or is actually in colors all around us. And that is seen specifically in the rainbow when it stops raining, and then all of a sudden, you see the sun. The sun, as the sun comes out, they as the sun comes out, you see that the rainbow or that light has different colors, and that's actually what light is. It's not a white beam of light. It actually is a spectrum of many colors. So what they figured out is that when they put that narrow beam of light, specifically using the hydrogen atom, they realized that it emitted colors, and it emitted four basic colors. And later on, other rays were discovered, such as infrared and ultraviolet and all that stuff. But for hydrogen, they realized that there was a color that was being emitted, and they saw it as purple, blue, yellow, and orange. And it's not that these are the only colors of the spectrum. It's just that these were the colors of the spectrum that were visible, that we can perceive. There are many other colors that we cannot perceive, or we perceive specific or specific colors, or specific at specific wavelengths. Like, for example, sunlight. We see sunlight as yellow, but that's not necessarily the color of the sun, right? That's just what our eyes can perceive, because it's easier for us to see the color yellow. And as I was saying, guys, so we have the colors, right? And those were the four basic colors that they saw. Later on, it was found out that this was there were more colors to the spectrum than those specific four colors. Okay, it says the emission of light spectrum was discovered when a narrow beam of light was passed through a prism and emitted four specific colors. This suggested that hydrogen exists in only very specific energy states. So that means that these four colors seen in hydrogen only happens at specific states. And that's true because that just means that this could vary from element to element. Okay, and then here we have Niels Bohr. And Niels Bohr, trying to explain this, proposed that hydrogen electrons can circle the nucleus at specific orbits. So Niels Bohr actually proposed that hydrogens were surrounded by energy levels. And in some cases, Bohr's theory was called as the planetary theory because it suggested that the electron orbits, specifically hydrogen, and it was so well accepted that this was just tried to scientists tried to apply this to other elements, but then they realized that there were some inconsistencies. But Niels Bohr's theory was very revolutionary and very important in the development of the new atomic theory or model as we know today. So Niels Bohr proposed, and we are looking at this kind of like when you shoot darts at a dartboard. He proposed that the electrons orbited in specific energy levels. So, for example, again, comparing it to the rungs of a ladder, like I did earlier, he proposed that the electrons were here, and this was in their lowest state, and that energy was applied to them, and they went up the energy levels as energy was applied. And I'm going to use red to illustrate the energy. So what Bohr's proposed is that the electron that is in this energy level, energy was applied to it, and that brought the electron to an excited state at a specific frequency, and it went up. And then as energy was applied, it went up the other energy level. Okay, so that's what Niels Bohr proposed, and he proposed this in about 1913. It says that the electrons orbit energy levels, and it says the electrons orbits or atomic energy levels can be compared to rungs of a ladder. The electrons cannot stand between specific energy levels. So what he also proposed was not only that as hydrogen electrons were had energy applied and were and they um and they went up energy levels, but he also said that they cannot stand here. Like you cannot find an electron between the or energy orbits. Okay, and what that means is that if you're standing on a ladder, you're either standing on one rung or another. You're not standing between them because you'd obviously fall off because you can't suspend in midair. The same thing is true with this. Electrons, which are the little red dots that I drew here, trying to say that the electrons cannot be here. Another thing that Niels Bohr proposed to explain this is that as I apply energy, and cause each electron to go up the energy level, right? As I apply energy and cause the electrons to go up the energy level. And let me erase these two little red dots here. He proposed that as energy or as they return to their ground state. So basically, I apply energy, they go up the ladder. But once I stop applying energy, they go back down the ladder. So it's in this state when they go back down the ladder that Niels Bohr proposed that as they go back down to their original ground state, energy or photons are emitted, so that the spectrum that we have here, the four colors, actually begin to start emitting once they go down the energy. And if you look at figure 1.9 in your book, they kind of use that green color to represent a photon. So he says that according to Niels Bohr's theory, the colors that scientists saw here happened because once the electrons went back to their original energy level, they started emitting these colors as energy. So this was a very important theory that helped further develop and understand the modern atomic model as we know it today. So hopefully this video was helpful, and I will see you guys in our next class. So bye.